In Chapter 9, we're going to go back and revisit systems of particles, and we're going to become more sophisticated in our analysis and our approach to systems of particles. But to start our discussion, I just want to go back and remind you that we've already looked at systems of particles, and the first time we really talked about a system and coupling and uncoupling the system, if you recall, was with our pulley system over here, where as long as M1 moved down 1 centimeter and M2 moved up 1 centimeter, we could consider M1 and M2 as one object and couple our system and calculate the acceleration of the system, and then we uncoupled, of course, to get the tension in the string. The tension in the string at that point was the glue holding the system together and was internal to our M1, M2 system. So we've already used this language and coupled and uncoupled, and believe it or not, we've also made an approximation to a system of particles. Whenever we've had a person in a problem or an object like a car, those objects are really systems of particles. So if we had a person walking or falling or doing anything, that person is really a head, arms, torso, legs, hands, feet, and what we did was simply make that person a point particle, and we did the same thing with a car. So all we did was ignore the wheels, the doors, the bumper, the windows, the fenders, the engine, all the pieces, and said, well, a car is going to the right and there's some force F, right, pushing the car to the right, and everything was a point particle. Well, we're going to do that again in Chapter 9 to understand our approximations that we used, and we're going to better understand it as saying that that point particle approximation is going to be where the center of mass point is, and I'm introducing new language here to you with center of mass, and I don't want to go into that in my introduction here, but keep that in mind. We're going to be talking about the center of mass as that point particle point. But generally, Chapter 9 is now going to give us a generalized approach to using F equals ma for any system of particles, whether it's a solid, a liquid, or a gas. Now we're not going to look at liquids or gases in this course, but we will look at, and please make sure you have in here the notations that I have, so you know that we will definitely continue to look at point particle systems and solids. So for our systems now, when we have a person, we're going to take particle 1, particle 2, particle 3, or for the car, and we can then calculate where the center of mass point is, that point particle approximation point. The best place to put that is for the system. Now we're going to go back and we're going to be talking, of course, about our internal forces, like the tension in the string holding those blocks together. All of these internal forces will be the glue holding the system together, and they will never conspire to just move the object. So you always have to have external forces if you're going to have the object actually translate left, right, up, or down. And we're going to start out on these first 2 pages of notes with just getting a general structure for Newton's second law, F equals ma, for having multiple particles in a system. And one of the aspects of using this system approach is to always consider what's in and what's out of the system. And as it turns out, that is arbitrary. So, for example, our 3-particle system that I have shown here at the top of the page. Let me erase some of my markings. This 3-particle system doesn't have to be analyzed as a 3-particle system. We can analyze it as a 2-particle system. So there's no rules that I couldn't say, okay, well, even though that first particle is part of the system, I'm only going to specify particle 2 and particle 3 as part of my system. Now, we are not going to have to worry about, well, why does that make sense? Why would you ignore particle 1? In many instances, you would be correct. That wouldn't make sense. So if a car is going forward, I'm not going to ignore particle 1 if that's the bumper and it's part of the car going forward. So what's in or out of the system often is really specified by the problem you're solving, and as I just said, something like ignoring the bumper would make no sense. The bottom line is, for us right now, we will not have to worry about does it make sense, doesn't it make sense, should I include it, shouldn't I include it, because the problems will specifically let us know what's in and what's out of the system. So the math that's involved here at the beginning, again, is a very generalized formal description of how to apply Newton's second law, F equals ma. In this case, the example is shown here, as I have in green, for the three-particle system that we have shown up here on the right. We can always use F equals ma for individual particles and calculate all of the forces. Now the internal forces count in terms of the movement of just particle A. So if I'm isolating particle A, I have to look at all the forces. The external force that is on particle 1 plus any of those internal forces will equal mass 1 times acceleration. And then, of course, we do the same thing for F2 and F3. The beauty of the coupled system, as you recall from our coupled system approach over here, is that once we couple the system, now those internal forces are going to cancel out because the system itself is thought of as an individual object. So that is really important. Let's go on to that. So now the system object, so some of the forces acting, let's add the word object because it's a system object. So the system object is now going to have all of the forces that are acting on the individual pieces, but what's very nice is all of the internal forces now cancel out. So we lose all of those internal forces, and then it's only the external forces that contribute to the motion of our system object. And let me put object in quotes here. Okay. So we're analyzing it as a single object. Of course, it's still made of these individual pieces. If we have a solid, so technically when we go from the gas to the liquid to the solid in physics, we call that a rigid body approximation, as I have stated down here, but really this is for solids, so let's put solids in there. So the pieces aren't moving. The bumper and the fenders aren't moving around relative to each other. It's a solid. In that case, there is no A1, A2, A3 subscript needed because they all have the same acceleration. When they all have the same acceleration, then we can factor all those A's out up here and just get 1A. We have M1 plus M2 plus M3 is our total mass. And now our system object can be thought of as a point particle where F equals ma gives us the motion of our system object. The center of mass will be that point particle, which we're going to talk about in our next page of notes, and m is the total mass of the system. So you don't need to know more than just this general understanding of where we're going. The specific problems we're solving for this chapter, and you can pause here if you want to finish copying the notations, but I'm going to go back for 1 second to the notion that for this chapter we will only be mathematically solving systems of point particles and solids, and we definitely are going to need a better understanding of how these systems were approximated as point particles and what this notion of center of mass is.